Okay, here we go. MBA 693. We're talking about descriptive statistics. Dennis Cross and LaSalle University. That's me. That's not me. I'm on the bottom. The guy looks like a human, not the guy up top that looks like a skull from, or a hieroglyph or something from Easter Island. So let's move on. Examining distributions is the first part. We look at the data. My computer is real slow. Okay. All right. So objective one, we're looking at the variables and values of variables. Typically, there's two categories of, or two types of variables, categorical types and quantitative types. And we're going to look at these types of, the categorical variables is as you would think, and the quantitative variables as you would think. That is a quantity and not a category. So looking at the data, let's collect and organize data. What we want to do is start investigating the data with a graph. Obviously, there's you know, in research, they call this thing multiple representations. Multiple representation is where you use visual data as well as descriptive data. So we're going to compute numerical summaries to describe the data and look at the overall patterns. That's the important thing, to look at the overall pattern, because then you can see if there's outliers, you can see if it's left skewed, you can see if it's right skewed, or whether it's normal and so forth. So let's see, cases. The object terms of a data set, like for instance, customers, cities, patients, cars, and so forth. A variable, a characteristic of a case. Example, profits, duration of a call, and so forth. Okay, here's an example. We're not going to go through the example, but there's a real estate example. In this real estate example, there are two types of variables. There's a quantitative variable, and that's where you take sort of the numbers, the quantities, right? You take numerical values for each, which can do arithmetic, like for instance, your age, your credit card balance, and so forth. That's quantity. The categorical variable is the places where you're dealing in groups or categories. For instance, gender. Gender is not a quantitative value. It's a male or a female. The brand of credit card, own a home, yes or no, these kind of things. So there's a major differences between quantitative and categorical variables. Here's another example, which I will not read, but there's a credit card example you can look at to see how to sort of identify each one of these characteristics. And so forth. You can see on the bottom quantitative, counting numbers, and the categorical variables for counting days of the week. Okay. Examine the data. Displaying distributions with graphs. Now, you've probably seen these kind of things before: bar graphs, pie charts, histograms, stem plots, time plots. Interpreting histograms and stem plots versus histograms. Okay. Important terms. Read it at your leisure. Purpose: summarize the data so you can read the characteristics of the distribution quickly. That's important, because sometimes you don't have to go through all the information. You don't have to go through all the analysis, but if you could just look at a plot, you could see what's going on. Like if you were in sales and you see the sales going up or the sales going down. These are the kind of things that, you know, people who don't have time to really dig down into the data, this is nice when you can display the categorical variables. Marital status example. You can see that the marital status in this case is the categorical variable. Okay, you can look down here: married, never married, divorced, widowed, and so forth. They're the categorical variables. What about the numerics? What about the quantitative values? You can see on the right-hand side, the count in millions, 116, 44, and so forth. So here we have a table that separates the categorical as well as the quantitative variables. Depending on the sophistication of the table, it could be called a contingency table or something along that line. Ways to chart categorical data by bar charts and pie charts. You've probably seen this a million times. Bar charts on the top. You can see that the folks who are married are higher in count as opposed to those never married, widowed, or divorced. Same thing with a pie chart, sort of thing. When I've worked in the past, I've had bosses who particularly liked one over the other. I'm not sure why. They both tell you the same thing, but everybody has their own preference. I had a boss one time that wanted every kind of visual available because he had no sort of quantitative skills. So he wanted to look at things and tell people what to do and boss them around based on the data visually. Okay, let's see. Okay, so here we have a online research example where we have the resources on the left-hand side, the count. You'll recall from statistics, if you never had statistics, N is the number of cases in a data set. For instance, in this particular data set, the resources for Google or Google Scholar were 406 entries, whether it's in a table, Excel chart, and so forth. And the total entries in this particular data set, we will say, is 552. Sometimes they're all cobbled together, and you have to use software to sort of separate them. I believe I had an email this week about how to separate males and females, because sometimes it's stuff scattered all over the place. In Excel, you can probably click up top to sort of separate the variables or sort of bring them together. SPSS, you'll use a different tool, and Jump, use a different tool. Depending on the tool you're familiar with, that's what you're going to use. I had a friend, I still have a friend, I think, that had spent 40 years in a large accounting firm, one of the big four, and we went to lunch one time. We were talking about data, and he was one of the large partners. Actually, it was PwC, and we're having a conversation about what kind of software he uses to do his analysis. And he said, "Wow, what are you talking about? I use Excel." I said, "What?" So there are people out there that don't get so sophisticated because they're so used to the things they've worked in the past. He grew up with Excel, so he likes Excel. Now, if he needed a little bit more detail or analysis, he'd obviously have to hand it out to his team to do different types of analysis. Some of the software packages, like, sort of, it used to be SPS, now it's Jump, and they, some people who are familiar with R and programming language, whatever they're used to, you can get the data you need. Now, in cases like Excel, it's very kludgy. If, for instance, when we talk about histograms, it's very, very difficult to do histograms in Excel. It's very unfriendly, but to Bill Gates's credit, which I don't like to give a lot of credit to because I'm not a Microsoft person, but there are software packages that sort of extend it beyond his capability in certain things. But if you grew up with Excel and you're familiar with Excel and it does the job and it gets the information you need, go for it. It just so happens that some of the newer software packages get to things more quickly. Okay, so let's move on. Bar graphs, you've seen this a million times as well. You can see that the bar on the left-hand side, Google has a greater market share than the library or Wikipedia or others. I'm not sure who goes to the library anymore besides me. The physical library, that is. Perhaps I like the aesthetics of the books and so forth, but you can see that, it's been part of the vernacular for the last, 10 years or so. Someone asked a question, well, you just Google it. You get on it, just Google it. Now, there's old school like me, or that'll actually go to the library, or maybe even go to. I think a lot of people this graph's a little bit more sort of. I don't know. I think Wikipedia has more presence than, say, the library. I think a lot of people go to Wikipedia for the quick and dirty, right? Somebody will say something to you, and you'll say, "Oh yeah, I know about that." And as soon as you get off the car, as soon as you walk out of the meeting, you jump to Wikipedia to try to be an expert in something. So Wikipedia, I think. And I'm not validating or vouching for this data here, but I think Wikipedia is much more popular than a library. But anyway, Google, everybody's Googling everything. That's why they're just such a monstrous company. So there's a bar graph, a pie chart, same kind of thing. Pareto chart. You can see here the two different, the same data. Okay, the same data, accidents per day of the week. You can see that the upper left is sorted. It was ranked in the paper. It's easier to analyze. You can see that, on Saturday, there was more accidents than on Monday. On the bottom, you can see that it's not sorted, and it's sort of a little bit more. Now this is a somewhat easy chart. You can see that Saturday on the bottom right is still the top dog. But if you were talking about a little bit more sophistication, a little bit more depth, more analysis, you'll see that the upper left is a little bit easier to analyze because it goes ascending from the greatest to the least. Now you can send it the other way as well, but there you go, Pareto charts. Okay, histogram, stem plots, time plots. Let's go for it. Okay, histogram. Histogram shows the number of individual data points. You can see here, I'm having a tough time reading this bottom here, but you can see that whatever that thing goes in the 1, 2, 3, 4, the fifth one has the largest frequency. What do you mean by frequency? That means the number of occurrences in the data set when they talk about frequency, not the frequency of a radio station, but the frequency of events or the frequency of the cases in that data set. And you also see the underlined equal size intervals. This is one of the problems when you try to set this up in Excel, is that you have to set these widths up in terms of bins. If anybody has done it, you probably rolling your eyes and say, yeah, I still do that, or yeah, I remember doing that. Now it's so much easier using other software packages. Okay, here we go. Now this is nightmare scenario. How to create a histogram. Now they're showing the Excel example. You go from 0 to 2. You have a count of 473. You can see that the range. I'm getting a message on my screen that says the case is unstable, so we're going to move on. So you can see that the range in the class is exactly the same. So in other words, 0 to 2, 2 to 4, 4 to 6.
Your voice is cutting out.
How about now?
You're still cutting out.
Can you hear me?
Yeah.
I can hear you now, yes.
Okay. Okay, you can see that the range in each one of these classes are exactly the same. In other words, 0 to 2, 2 to 4, 4 to 8, 6 to 8, so forth. It's 2. And in Excel, you have to set these kind of things up. Okay, and you can see the reason is because you want some consistency and equal width across each one of these categories. However, once you do set this up, you can see that we're getting the same sort of histogram that we had in the previous slide or any other software you have. Again, the pattern of being consistent in the width of the range is what's important, because you need to be consistent. You can see with consistency that the third event here, the rate on the bottom, you can see that that's the largest count. Okay, so depending on the type of software you use a histogram, the overall importance of the histogram is that you have some sort of idea what the data looks like, and you can see that when we start moving up the rate, that we start topping off. Okay, this is the same kind of thing that I had just said. Yeah, that's an interesting thing. There isn't a unique or perfect solution. Why is that? Because you as the user or as the developer, have to decide the width of these classes. And sometimes you're wrong. When I say wrong, I don't mean wrong that you didn't do it right. I mean wrong that perhaps your selection of the width of the class is too wide or it's too short, because you're not sort of getting to the point of any outliers or so forth. So it's not perfect, but it gives you a sort of a high level overview on what's going on with the data. And if you have time, and most people do not have time, is you play with this sort of width of the class, and maybe you get some things that you analyze that you really didn't know. Like if you were in sales and you sort of see a niche market, and the only way you get that is you start breaking down categories and demographics. Well, you needed some time to do that. A lot of times in sales, at least when I was working in Washington, there was entire organizations just dedicated to sales, and they were so busy doing the sales piece, they didn't have time to do the analysis. So if you couldn't do it in-house, they would send it out to some sort of the consulting firms. That's why Washington, if anybody's ever worked in Washington, and I have, anybody who's ever worked in Washington is typically working. There's very, very low unemployment for the educated class. If you want a job, you can get one in Washington. The problem is, we're on a little side topic here, very expensive to live down there. So even though you get more salary, you're going to pay more to live there. But anyway, if you want a job and you don't have a job where you're at, move to Washington. A lot of consulting firms, a lot of people who do this data analysis and statistical stuff, because a lot of sales folks just don't have time or the knowledge to do it. Okay, so same sort of thing here, different kind of analysis. We're talking about stem and leaf plots. You can see on the left-hand side, we have the stems going down here from the left-hand side. On the right-hand side, they're the leaves. And if we stack those up, if we could stack those up, essentially you become a histogram. So it's the same kind of data, it's only represented differently. It's just like I say, how you want to look at the data, how you or how your boss or how your client, and importantly, the client's paying the bill. If the clients wants to analyze or wants a report that wants to look at graphs a certain way, well, then learn it and how to do it and make the report accordingly. Okay, blah, blah, blah. I won't read that. There you go. I'll just pause on the screen. There we go. Same kind of thing. Stems on the left, leaves on the right. And you can see what we're doing is analyzing 12 data values here. We're creating the stem and leaf plot on the right-hand side. The methodology on how to do that is sequenced 1 through 4. Okay, here's an example of T-bill interest rates over here. Get something on my screen. We're writing the stems, and then we're adding the leaves, and then we're ordering the leaves. And we're doing that ordering the leaves particularly because we want to see things in sequential order. We start out at 0, 1, 0, 1, 0, 1, 0, 1, 0, 3, and so forth. Then we go all the way down to, let's see, let me see one that's a little bit different. See this one right here, 8. Before we ordered them, we had 8, 6, 4, 86, and 84 that represents. And then over on the right-hand side, we'd order them for 84 and 86. So in other words, the difference between the middle B stem and leaf plot and the C stem and leaf plot is one is unordered and one is not ordered. Okay, this is a good point. Obviously, if we go back one, we can see that it's pretty simple. If we have a very large data set, stem plots do not work with large data sets. Now imagine trying to do that. Imagine trying to do this with an extremely large data set. A couple of years ago, when I was teaching the undergraduate class at LaSalle, we were, I think it was 2016. Yeah, it was 2016. We were analyzing the poll results from all 50 states. And what we did was we downloaded the data from each state and we did some statistical analysis and made prediction of who was going to win the election. Well, that was interesting. One thing I should point out that when you do these kind of things, you really got to put your bias out. You got to sort of not be emotionally attached to what the data actually says. And as an analyst or a statistician, one of the first things you are taught, not in school, but what you're taught in the real world is your job is not to pick winners. Your job is not to do the analysis. Are we still here?
Yes.
Yes, sir.
Okay, I get dropped off for a second. Okay, so let's just continue. So your job is to look at the data, not get emotionally attached. So if your job is working for a political consultant, your job is not to pick winners. Your job is to do the analysis. So one of the things that at least my undergraduate students, they failed in that they were sort of picking winners and losers. And I said, no, you don't get paid to pick winners and losers. Your job is to do the analysis. Whether the analysis disagrees with what your own emotional attachment is, that has nothing to do with analyzing the data. So when you're dealing with large data sets, stem and leaf plots, it will be very difficult. And in the case of a very large data set would be an example of when we started analyzing political data. Now it's political data. We can analyze sort of car accidents, which is an extremely large data set. There's data sets in the health sciences that are just make your head spin. They're just millions and millions and millions of entries. One of the limitations I teach the undergrads, when we were analyzing this data set, the Excel could only take so many entries. So it's not a matter of just getting data from Excel. There's all kinds of ways to get data that is huge. But the important thing here, since we're on the slide about stem and leaf plots, stem plots do not work well on large data sets. And there's all kinds of things that go on, but that's important. But for us, we're trying to learn these things, or we're trying to sort of review these things. We just keep it simple. Stem plots are sort of for large, small data sets. Talk about interpreting histograms. You can see that the shape is important. You're talking about the spread. Look at the how the shape is. It'd be very difficult on the left-hand side of the histogram if you're trying to connect things. Like you can see the red line. You can see that we're connecting things at the center. And again, the center is sort of arbitrary because you pick the width of the case of the width of the histogram. Sort of it's arbitrary, but looking at the red line, it's very difficult to find out where the middle is. However, if you normalize it or smooth it, you can see the overall pattern of the distribution is sort of some sort of oval or ellipse, and you can see where the middle of the data is. Now, again, it's not perfect. We're just looking at things from a high level, but you can see that the right-hand side is a little bit more appropriate for interpreting histograms than the left-hand side. Okay, you've probably seen this from doing the exercise this week, skewed right, skewed left, symmetric. Symmetric here is, you can, obviously it's symmetric from the center, and anybody who has done any normal curve analysis, you can see that sort of represents a normal pattern. Normal, when I say normal, I mean normal or a Gaussian curve. Look at this one here, we have two peaks. How do you know which one's appropriate? You really don't know. But the histogram shows that there's sort of a peak in at D and sort of a peak at O, and since it's lopped off here, you don't know if this thing goes up to forever. For instance, if we were talking about, I don't know if anybody follows the commodities, the COMEX, you can see over the last couple of weeks, if not month, the price of gold and silver. I mean, if you look at this thing, you don't know what window it is. If you look at the price of gold and silver over the last month, or actually over the last couple of years, you had an increase of like several 100%. So I always get a kick out of my friends who work on Wall Street talking about, this latest stock. But however, one of the greatest increases in finance is the precious metals industry. You just got to look at it. Now they had a long time of flat growth. However, you can see that it has peaks and valleys. And the question is, what does this represent? You don't know if it represents sort of a cyclical or a seasonal activity in precious metals or whatever this data represents. And I have no idea what this data represents, but you can see that two peaks, and the graph starts with, so what does it say? The graph starts with a symmetric portion and is flat in the middle and increases at the end. Yeah, obviously. And depending on the data you're analyzing, will be important. So if you're analyzing a trend and this is cyclical, this D was a year ago and this O was a year ago, you can see that the thing is seasonal. And if you were looking for investment, you want to purchase the thing off season. In other words, this flat value from G to K, that's where you want to buy. And you sort of want to get out of the market, C, D, and E, or M and O. Okay. Now let's look at this, outliers. Outliers. Always look for outliers and try to explain them. So here we got, what do we have? We have percent of state residents aged 68 and over. Yeah, so you can see we have outliers here, and we have Alaska and Florida. If anybody's been to Alaska, you can see there's a lot of wacky people up there, and you see in Florida there's a lot of blue hairs. I remember when I worked at in Boca for Siemens, I was warned when I went through a green light to make sure you didn't just go through the green light without looking. Because the older folks who lived down there really either ignored the red lights or just sort of had some color blindness and went through the lights. So you may go through a green light thinking you're perfectly fine, and then you get side swipe. So I understand the Florida thing. The Alaska thing I don't quite get, because there's a lot of sort of different kind of people up there. There's young people, there's middle-aged people, there's older people. I'm not sure. Again, whether this data set's real or not, I'm not sure. They're probably just using an example for looking at gaps and outliers. So time plots. We, in the undergraduate world, I spend at least 4 weeks on decision-making and talking about analyzing data in one of the courses, and 2 weeks is on time plots and how this thing trends. In fact, two of the weeks is actually on seasonal variation and cyclical events. You can see that on the upper left-hand side is obvious. I mean, this is you don't need me to sort of reiterate this. You can see that the trend is going upward, and whatever this represents, you can see whatever it is. Again, we're going back to the financial world. If this is a stock portfolio, this is kind of a good thing that it's going up. On the bottom right, you can see that this is a cyclical pattern, and it has seasonal variations. How do I know that? Because you can see the peaks and the valleys are repetitive at certain intervals. And so if this were again, if it were a financial instrument, even though it's going up, you'd want to sell it to high, buy it to low. This, I don't know, this is not a graph on housing prices, but over the years, housing prices has increased. In the old days, I think back in the 60s and the 70s, there was a seasonal variation. I remember many conversations that people would put their house up for sale in the spring, sell them in the summer so their kids can go to school in fall at whatever location they were moving to. So there was a seasonal variation or component to that. Today, it's a little bit more challenging and complex because housing prices are all over the place. People want to move, they want to get out of the city, or they just want to move. So that sort of the variations are a little bit more complex than what we're seeing right here. But you can see the upper left, there's a trend moving upward that has a pattern that is somewhat predictable, even though we have peaks and valleys. And the bottom one is a little bit more predictable because there's a seasonal variation component that sort of gives you sort of an outline of when to sort of get out and get in. Let's see. Yeah, okay. We got oranges. Obviously, that has a seasonal component as well. Selling oranges. Let's see. Yeah. Again, we're back to this T-bill interest rate sort of thing, and we're representing this thing with the graph up top and a histogram on the bottom. Okay, this is important because I've seen this a lot in my career where the scales are just wacky. Like, look at the bottom middle. Like, why would you start a graph with the left-hand y-axis starting at 120? It just doesn't make any sense to me. Now, the way you get around that is you start at 0 and you work. You maybe have to scale it back. But that if I saw a report like this on a professional level, somebody sent that to me or I read it, I would say that that person that has not necessarily intentionally mischaracterized the data, but it's certainly not a professional way to do it. You really got to start at 0. Maybe the graph has to be really small, or maybe you're just or you're looking at a snapshot, but you need to put that in the verbiage when you put something like that in a report or something. You've got to make sure you're explicit in the verbiage that make sure you understand that we're starting out at 120 on the y-axis at 1940 or 1942. All right, so let's examine data with numbers. Now, you've probably seen this before, the 5-number summary, the mean, median, mode, quartile, standard deviation, and so forth. I had an email about scales and what the variations and deviations were. This is where sort of you can look at that and analyze that and make a decision. Obviously, the mean is what typically a normal person would say is an average, but somehow when you go to college or you take a high level of math class, they change it to mean. Whatever, same thing. So the average is the mean. Now we're adding all the values together, and we're taking we're dividing by the total. So sum of start times is 391 divided by 24 because there's 24 cases, and therefore the average is 16.292 days. And we're going back to the undergraduate education. I was very much of a stickler on 4 significant figures. The reason is because sometimes students would look at the data and just sort of do it in their head and say, oh, it's 16.2. No, I needed them to go through the process on how to do that. You guys have, again, been vetted. You already have an undergraduate degree. You're in graduate school. We don't need to get into the vernacular. And you'll see in the next couple of slides, there's a lot of mathematical formulas, and I put them on there just for consistency. However, you're not expected to memorize any of these kind of formulas. You could just do these things on your calculator. You can do them on your phone. You can do them in Excel. You can do them in R. You can do them whatever you want. I put them in there just for consistency. This is a perfect example right here. So we have a sort of a bunch of data here, black females, black males, so forth. And there's the formula. The X bar is actually the bar over top means it's the average. So the X mean or the X bar, depending on the book you have, it'll call it something different. You take the sum of these things, which is what this here. We got X1, X2 plus Xn. And what that N means, it's the number of elements in the data set. So we take the first entry, X1, X2, X3, X4, X5, all the way to Xn. And whatever the N is, if it's 127 elements in a data set, that is the N. So we'd go to 125, 126, 127 would be the last entry, and we would divide it by 127. That's the average, that's the mean. A little bit more sophisticated language here on the right-hand side, 1 divided by N. You can see that, I can't see my mouse, but okay. You can see the end on the left-hand side of the equation and the N on the right-hand side of the equation. It's the same thing. The only thing we did was that sigma values. We said we started at I equals 1 to N. That's just the fancy, smancy statistical way or mathematical way to say all the N values go from 1 to N. And an example I had given a couple minutes ago is 127. Now we just sum those up. The sigma, that sigma symbol there means we're adding things up. So we're adding up all the data sets from 1 X sub 1 to X sub 127, and we're dividing it by N. So the left-hand side and the right-hand side are the exact same formula, except one is a little bit more different format than the other. And you can see how we figured this out. 262,940 divided by 15, and we come up with the number of 17,000 and change. All right, now let's talk about center of mass or the median. The median is the middle one. You can see on the left-hand side, we have a data set that has 25 entries. Real simple. When you have 25 entries, you just take the middle one, the 13th one, because 25 divided by there's 12 on the top, 12 on the bottom, and 1 in the middle, and it's 3.4. On the right-hand side, a little bit more challenging, but same kind of thing. We have 24 data points. So what we do is we take the middle two and just take the average. Same kind of thing. Left-hand side is odd. We just take the middle one. The right-hand side, we take the two middle ones and divide it by 2. Same thing. All right, let's look at mean, median, symmetrical values. Now, the Gaussian curve, or what we would call the normal curve, is the middle one where the mean and the median are equal. And you can see the left skewed, the mean is left of the median, and the right skewed is the mean is to the right of the median. Okay. All right. Now, so you could see this issue with outliers. Outliers this is another thing that I try to teach to undergrads, is that just because it looks like it's weird and away from the data, you just don't call it an outlier. Outlier has specific rules. In this case, they're saying that it's an outlier. We don't have enough information to really determine that at this point, but it has specific rules, and we'll see that in, I think, a slide or two. Unless I took it out, we'll see. Okay, so mean and median of symmetry, you can see that the top is symmetric, where the X bar is 3.4 and M is 3.4. In other words, the mean and the median are the same. As we went back a couple slides, you could see that that was the representation of what the Gaussian curve was. And on the right skewed distribution, you can see that X bar is greater than M. So in other words, the mean is pulled toward the skew. It's skewed right. Okay, these are some sort of characteristics of mean versus median. Mean is not resistant to outliers. The median is very resistant. So in other words, there's reasons why you use each of these sort of 5 number summaries. Some things, you know, will characterize the data one way, and maybe you have to drill down a little bit to see really what's going on. All right, I'm not reading that slide. I'm not reading that slide. All right, percentiles, let's look at this. I had a couple questions over the week on percentiles. Most of them were valid because Canvas sort of, I don't know what they did. I don't know what range, right? Q. Can you hear me? I'm sorry.
You're breaking up again.
Hello? Can you hear me?
Yeah, yeah.
Hello?
Yeah, I can hear you.
You're
Hello?
back. I can hear you again.
Yeah.
Can you hear me? Okay, let's move on. So quartiles, Q3 minus Q1 is the median.
Sorry, I can't hear you again.
From the same issues that we had last slide, the Q3 minus Q1 is the median, and you can see the box plot. We have a maximum of 6.1 in this example, and the smallest is 0.6. Again, if you've had issues with this on Canvas, I think I resolved those. Can you hear me? Getting some messages that you can hear me. Okay, thank you. I'm getting yes. Thank you very much. This is going to be great if you review this and trying to figure out what I'm talking about. But if you're reviewing it after the fact, I have issues with going in and out and the sound. So again, let me go back one. We're talking about measures of quartiles. There's the quartile, first quartile Q1 and Q2. The difference between the two is the median. And there's the box plot. Okay, same kind of thing. One of them is sort of organized, you know, numerically. The box plot really gives you a visualization of what's going on. Okay, same kind of thing. You can see that the top left is skewed right, and you can see that by the by the diagram up here, it's skewed right, and you can see by this diagram up here, it's skewed left. Again, going back to the undergraduate courses, sometimes I would just give figures and say which one's skewed right and which one's skewed left. Sort of a give me, you know, free points, but there are people that sort of don't do the work until the last minute and don't get it, so easy points were thrown away. Okay. The data we had a couple slides ago, you can see that the plots for the 4 categories of black female, white female, black male, white male are indicated here, and how much folks earn. You can see the bottom tier is somewhere around 18,000 and change, and the top tier is in the sort of mid-20s. So there's a side-by-side box plot of this data set from National Bank, wherever that's at. Okay, so again, I talked about outliers, and just don't rely on what you see on the screen as outliers. There's specific rules for outliers, and I believe it's on the next slide if my memory serves me correctly. Nope. Again, there's another visualization on how he calculated this this problem from the last couple slides, and of course Q3 minus Q1 is the median value. Okay. So the measure of the spread, standard deviation. There's the formula for standard deviation and variance. You can see that the standard deviation on the bottom is S equals, you know, this radical and all these kind of crazy numbers and formulas. And the square of that S value is known as the variance. In other words, how, you know, how this thing varies over time. And it has a specific number. And you can see that the median on the left-hand graph has a mean of plus or minus 1 standard deviation. And you'll see in the next couple slides of what that means. Okay, degrees of freedom, we're moving on, no, let's stay here for a second. Yeah, so S is 0 only when all observations have the same value and there's no spread. So there's no spread at all when S is equal to 0, and it's not resistant to outliers. Okay, let's move on. So we have a bunch of things here, 68, 95, 99.7 rule. I spend a whole day on this when I'm teaching an undergrad. Not that it's real complicated, but it's very interesting on how it's applied in the real world and how much people spend money to get data and analysis. A bunch of other things here, standard deviation, normal distribution, and so forth. I believe this is the last part of the slide deck that we're going to do. We're going to cover it as quickly as possible because I try to squeeze things into an hour if I can and not go beyond, because people's times are important, and people don't want to listen to me more than an hour. Actually, they don't want to listen more than 10 minutes, but let's move on. I digress. Density curves. A density curve is a mathematical model of a distribution. Distribution is what we have on the bottom. We have the bottom distribution. You can see that what is accounted for are the shaded bars that go beyond the curve, and the one on the right is the area under the curve with the bars that go beyond the curve, not counted for. I remember having a bunch of different calculus courses, and we got into this in so much detail. I get nightmares thinking about it. But on the bottom left, we got a grade equivalency vocabulary scores. Bottom right, grade equivalent vocabulary scores. The difference is the sampling. If you sample more closely, you're going to get more close to your actual value. And the reason the sampling is important is because when we talk about surveys and things like that, it can get very costly. So a density curve is, on a high level, is the area that's represented under the curve, that red part, that's the area. And you may recall from prior training that the area under a normal curve equals 1, and a normal curve, which means that if we split the curve down the middle, on the left-hand side equals 0.5 of the total area. On the right-hand side, it's 0.5 of the total area, which is why people use normal curves all the time. So it's very simple. You could just cut it down the middle and figure out how much we need, what the proportions is for the observations. And these I don't know what we call it, density curves, but even further, distributions. I'd rather use distributions. You can see distributions or density curves. On the upper top, we got a square one that has some consistency. You can see that to the left of that, there's nothing. To the right of that, there's nothing. And all the things that we're concerned about are within that box. And then, of course, we have left skewed, right skewed, and some wacky thing on the bottom. We don't know what it is, but it is what it is. So here this is a sort of a repetition of what we've talked about in the past, the differences between the median and the mean, or how it's represented in different things. You can see again in the middle, I'm sorry, the right-hand side, that the median and mean are exactly the same value. And depending on if it's left skewed or right skewed, will be to the right and to another curve that's not represented on that screen. It's a couple screens ago. Now here we go. Normal distributions, or Gaussian curve, right? So the mean, as represented by that thing you think looks like a U, in Greek it's called mu, and then the standard deviation looks like a sort of little silly S, that's a sigma, and we need both the mu and the sigma to represent, you know, the pattern of normal distributions. You can see that N with parentheses mu and sigma. That's typically how you represent mathematically what a curve looks like. And the spread, when we talked about spread, you can see the sigma on the bottom left curve is sort of wider than the one on the right-hand side. And there's that wonderful mathematical formula you're all looking for. There it is. And E represents this number here, the natural log. My background is engineering, so I kind of care about that. Most people do not. And there's the value of pi. But you can see what most importantly on the screen is that the wider or the larger value of sigma represents the spread, or the how wide the distribution is between subsequent sigma points. In other words, a couple slides ago, we had something plus or minus 1 standard deviation. That's where this comes in. So we could see, you can see the bottom left too, that there's a sort of a wider population of sort of data that's spread out. Whereas if you were doing sort of micro targeting marketing, the one on the right would be more preferable, because if you're selling widgets or something that's very unique, you want to sort of target market your folks so you're not wasting time in advertising. You could sort of set your price. So obviously, maybe not obviously, but on the right-hand side, it's going to cost you more money to sort of analyze that data, because it's a tighter space as opposed to the left-hand side. If anybody's walked through the mall in the past and you've seen people walking around with clipboards, and they ask you, you know, how do you rate this perfume? Well, that's sort of a very silly sampling. Obviously, very cheap to do. They're paying these folks very little, and you don't know, you know, you're walking through the mall, you see all kinds of misfits walking around, and including yourself, maybe myself. You don't know who these people are. So why were you asking them if, you know, you prefer the type of perfume? I have no clue. I tend to walk through these things and give them the opposite answer of what they're looking for. So if they say, how do you think this smells? It may smell perfectly fine, but I can say, oh, this is horrible. Only because that's, I just have to happen to have a little bit of fun. But somebody is actually looking at this data and taking it seriously. And that's the left-hand graph in this slide. And the right-hand side, it's a little bit more refined. They're sort of picking their audience. They're not walking through malls. All right, I digress, but that's what I do. Here's a family of density curves. In other words, we're, again, going back to this spread, this sigma. Here's the family of spreading sigmas. We have 2, 4, and 6, okay? And the bottom we have different mu's. We have 10, 15, and 20. Notice the differences. The center of these graphs on the bottom are at different locations. Whereas on the top, the centers are the same because the mu is 15. So they're all 15. They're all a mu of 15. The difference is the sigma is spread out between 2, 4, and 6. Okay. So that's what happens when you change the characteristics of the mu and the sigma. The 68, 95, 99.7 rule is exactly what I had sort of discussed a couple slides ago about, you know, how much money you want to pay to get more accuracy. So when we're talking about 68, 95, 99.7 rule, we're talking about the level of accuracy. Obviously, from a couple slides ago, we talked about that widespread where you're walking through a mall to get things. Let's just say that that's the 68%. However, if you start sort of tacking on some more money to get a real server, you're going to tighten it up. And it should be inherently obvious that if you do that kind of thing, you got to have more sophisticated tools, and it's going to cost you a lot more money to do that. That's why people go through malls to get surveys, because it's a quick way of getting data. It's a quick way. Now, maybe your product, I don't know, maybe you're selling some sort of silly pen that looks pretty. maybe a good idea to go to a mall to have somebody to pay, very cheaply to get sort of thing. People walking through the mall, they say, oh yeah, that's a pretty cool pen. I'll pay $2 for that. Maybe that's, why do you need sort of sophisticated algorithms to check out that kind of sale? You're not going to do it. So somebody walking through a mall with a clipboard is perfect. But for most of us, we're not doing that kind of business. Well, maybe we are, but I think in most professional venues, they're not. You're working for sort of a large company, they're not going through malls to get data. So that's a high-level overview on what the 68, 95, 99.7 rules is, and there's just mathematical tools to differentiate between those three. All right, I think we did. Okay, now, so in this case, difference between the left-hand side and the right-hand side is the left-hand side is using actual values. So every problem you work on has to have a different mu and a different sigma. In this particular data set, it looks like we have 64.5 as a mean and a 2.5 spread on the sigma. However, if you normalize things, if you normalize your data by finding what's called the z-score, you find the z-score, the mean is always 0. And the standard deviations are always sort of plus and minus 1, plus and minus 2, plus and minus 3, and so forth. It makes life easier if you're doing the analysis, if you do the z-scores. And there's a formula to do the z-scores. You can do them in Excel real quickly. And when I teach the undergraduates, you can just do it in Excel. You can do it in any software package, but you can do this real simply in Excel. How do you do that? You take the data point minus mu divided by the sigma, and that's your point. That's your data point. That's your z-score for that data piece. And there's a couple examples there. You can check it out. And I mentioned a couple slides ago, or 5 or 10 minutes ago, there is a difference. There is sort of a rule on what a outlier is, and the rule is that if the z-score is plus or minus greater than plus or minus 3, it's an outlier. So there's a specific rule on how you determine an outlier, not just looking at the visual. And here's an example they give of a couple slides ago, 64.5 mean, 2.5 standard deviations, and I go through all the iterations on how to do that. And you can see the graph up top. Notice that it says area, question mark, question mark, question mark. The area, what we're talking about is the area under the curve for that particular problem. You can see the pink is, I don't know, it's above the 0 mean point, so you know it's at least 50%. So let's just say it's 75 or 67. And then that would mean the area under the curve, no, it tells me right here, I'm sorry. It says area equals 90 or 0.9. That means 90% of the area under this curve is pink. And the area above that obviously would have to be 0.1 because the entire area under the curve from negative infinity to positive infinity must be 1. So if you take 1 minus 0.9, you have to get 0.10. And I don't think people do this today. I mean, when I went to school, we had tables in the back of the books. Every sort of mathematical book had tables in the back, and sometimes there'd be 20, 30, 40 pages, and you'd have to look these things up. You'd have to look them up on a table and, go down the bottom, go to the right, and find out what the z-score is, and then do all that kind of thing. I'm not sure. The last book I saw, or at least that I had purchased new a couple of years ago, I think they had like 2 tables in the back of the book. But people don't do that today. You can just do it on your calculator, do it in Excel, you can do it in R, you can do it in SPSS, you can do it in Jump. You can probably do it on your computer. There it is. But anyway, if the world ends and you don't have a computer, you don't have electronics, at least you'll have a table, you can look it up. I'm not sure why you want to look it up if the world ends, but there it is. And so they go through an example on how to find these kind of things, and there it is, 0.8413. Okay, have fun. Again, the z-score can be used to determine what an outlier is. And sometimes you need to lop off those outliers if we're going to do analysis. Like the example we had about 15 or 20 minutes ago about the 50 states, if you were doing some detailed analysis and didn't want to count for Florida and Alaska, you would lop those off and do the analysis without those outliers staying in there, if they were outliers actually. So this is the sort of same kind of thing that I had mentioned earlier. Because the area on the right part of Z is some sort of value, just to say it's 0.9, and then we know that the area under the curve is 1, we can just take the difference of 1 minus 0.9, and that would equal the left-hand side, in this case would be 0.1. Same kind of business, a little bit more examples. I'll leave that up there for your leisure to check it out. It says table 1, that was a couple slides ago. Another example on NCAA qualifiers. I think the book they used to use for undergraduate, they used to use this example over and over again because people like sports, so they like to analyze sports data. Okay. Same kind of business here. We're talking about how to find z-scores. There's the formula again. Z equals the data point minus the mu of the data set divided by sigma. And same sort of business, trying to find the opposite. In other words, we go from z-score backwards and try to find this thing. There we go, opposite table. The inverse normal calculations. And then there's another example of inverse calculations. I think, oh no, we got one more slide, the normal quartile plot. We can access data that way as well. And just real quickly, let's look at the graph. You can see that the upper left-hand side, it's relatively safe. It's a pretty large data set. Probably, if I count those points up, it's probably 100 or so, 100 data points. But you can see that it's sort of straight, and in the quartile plot will tell you that the distribution is roughly normal. I mean, nothing is exactly normal, right? I mean, it's a real world, but these are theoretical concepts. But you can see how straight that line is in the upper left. So it's roughly normal, the data set, whatever they're analyzing here. And then the normal quartile plot on the bottom is sort of has some skewness because it's not as straight as the upper left. So let me close down this presentation on descriptive statistics, and hopefully you've got something out of that. 1 second.